Okay, AP Chem, I'm going to do another problem for you that is a limiting reactants problem, and we're going to use a BCA chart. The problem states, the reaction between potassium chlorate and red phosphorus take place when you strike a match on a matchbox. If you were to react 5.00 grams of potassium chlorate with 5.00 grams of red phosphorus, what mass of tetraphosphorus decaoxide could be produced? How much potassium chlorate and red phosphorus remains after the reaction is complete? Well, if you know those square cardboard boxes that have that red edge on it that you strike the match on it, that's what this problem's talking about. If you notice, they're asking us for a lot of information, but we do one BCA chart, and that's going to give us all the information that we need. First thing, let's try to figure out what these compounds are so we can get the balanced chemical equation. Potassium chlorate. Potassium and chlorate is an ionic compound. These are both going to be in solid state, but I'm not going to worry about the state of matter because that's not pertinent to this problem. Red phosphorus is not one that you'd really be expected to know, but red phosphorus has the formula P4. And then our products are going to be tetraphosphorus decaoxide. Tetra is 4, deca is 10. The other things that are left over that have not been accounted for are KCl. Again, that's a tough one. You wouldn't necessarily be expected to know the reactants and the products. You would probably be given this chemical reaction at this point in time in your chemistry career. So if you remember, the first thing we need to do is balance it. Well, right now, K, C, and Cl are balanced, and phosphorus is balanced. The tricky one here is look at this oxygen. I've got 10 here and 3 here. The lowest common denominator for 10 and 3 are each other. So I'm going to have to put a 3 here, and I'm going to have to put a 10 here. That unbalances the K and the Cl and the phosphorus, so I'm going to go ahead and give them some coefficients too, like such. Remember, BCA charts always have to have the befores in moles. It's all in moles. You could also use molecules or atoms or formula units, but that's not going to be as common because in chemistry class, we can never come across single pieces of stuff. We only talk about that theoretically. So let's change potassium chlorate from grams to moles by dividing by the molar mass. The molar mass is 122.55. I added 1 potassium, 1 chlorine, and 3 oxygens together. And the mole start value is 0.04080 moles. Let's change P4. It's not P, so we have to multiply P by 4 in order to get the molar mass of 123.88. So the starting value is 0.04040 moles. Before the reaction starts, we don't have any products. Now remember, in the change column, the reactants will get a minus and the products will get a plus. If one of the reactants gets a minus, all of them have to get a minus. If one of the products gets a plus, they all have to get a plus. If you give a plus to the products, you have to give a minus to the reactants and vice versa. We know the products need to be a plus because you can't have less than 0 as a quantity. So we can only get more products. We started with 0, we're going to create some products. Now you might say to yourself, this is going to be a mole ratio of 10:3. There's about the same quantity of potassium chlorate as there is of red phosphorus. So is that going to be confusing or what? But because of the mole ratio, because it takes 10 times the amount of potassium chlorate and 3 times the amount of, we know we need a lot more potassium chlorate. We don't have a lot more potassium chlorate. So I'm going to guess that that's the limiting reactant. Let's finish our change column first. And let's set this equal to 0. I have about the same amount. I need lots more potassium chlorate. So I'm going to guess that that is the value for x. So my algebra problem becomes, let's solve for x here. Remember, it would be before minus change equals after. So 0.04080 equals 10x, and then x is going to equal 0.04080. That's my value for x that I can plug into all of them. So 0.04080 minus 10x equals 0. 0.04040 minus 3x. I'm going to write that down for you so you don't get confused. So that's how much red phosphorus is going to be left over. Now, to figure out how much tetraphosphorus decaoxide we produce, we just take the value for x and multiply it by 3. So 3x equals 0.01224 moles. And the value for 10x is 0.04080. So let's analyze what happened here. We reacted 5 grams of each together. The potassium chlorate was all used up and there's none left over after the reaction's complete. The red phosphorus was not used up and there's 0.02816 moles of it left over. We produced 0.01224 moles of tetraphosphorus decaoxide, and we also produced 0.04080 moles of potassium chloride. That's what's left in the container after everything is done. If you want to change these to moles, from moles to grams, if they asked you to change them from moles to grams, you would just multiply by the molar mass. So in this case, 0.02816 multiplied by the molar mass of 123.88 grams per mole. This guy here, 0.01224 moles. And that's going to be 283.88 grams per mole. Let's add the unit, the labels in there so we don't get confused. And that's going to give us a mass if they asked for it. But if they didn't ask for it, we don't necessarily need to worry about that. So that is just one additional limiting reactants problem for you to try to wrap your brain around the BCA chart.